Alright, one more video about model interactions. Let's see, here the antibody platform prediction is off. It's the edge of carbon, it's not an antibody platform. So we'll want to get rid of it. First thing we'll try is to give model competition to the antibody platform model as well. So let's set it to absorb, but not to emit, because in those regions where it's correctly predicting antibodies, it's the only thing there, so we don't need to compete with carbon and membrane. But over here, the carbon is actually better. So by setting it to absorb the competition from the membrane and the carbon model, we should get rid of those predictions. Let's see if it actually works. There we go. So that's a start. But still, it's quite some stuff here and there. One easy way of getting rid of it is ignoring it. That sounds a bit silly, but when you look at these antibody platforms over here, and you browse the volume a bit, you can see that there's multiple consecutive slices where these platforms are predicted as platforms. So if in the final 3D segmentation we threshold and then look at particles sorted by volume, those ones will be a lot bigger than, for instance, this spurious little peak over here, which is not seen in the next slice, right? So just that there's some pink blobs here and there where we might not want them isn't necessarily a problem. It's only a problem if that prediction is there in multiple consecutive slices. So maybe that can also be a fix over here. So there's a pink blob, and then in the next slice there's actually another pink blob. So it's not what we want. So this one is a problem. It's close to carbon, and it also absorbs the competition from carbon, and you can see that we have this overlap artifact over here. So at the edges of the data, the predictions can be a bit off if the overlap is low. So let's set the overlap to the maximum value to get the carbon model to work better, and we've put the threshold to 0, which is not great, so let's set that to 0.5 or something like that. And this is only for visualization, by the way, so the threshold that you set here does not affect the emission and absorption competition. It can affect the interactions one, but we'll get to that in a minute. But anyway, we've now fixed this bit. Let's actually crop it so that we can get that feedback a little bit quicker. Overlap 0, and we get some membrane stuff over there, as you can see. And then the overlap to the maximum. The carbon model works better. Because of that, we get rid of the antibody platforms. So usually when I process an entire data set, say 100 tomograms overnight, or just as a background process, I set all these overlap values to the maximum, because that's usually better, and then you can get rid of these artifacts. So we've got some pink stuff over here at a very low threshold, so usually we would also set that a bit higher. So that's not too much of a problem. Let's see how it does now. Okay, so we get rid of most of the pink stuff. There is still some over here, which is good, and then some stuff over here which we don't really like, and also there. Another easy way of getting rid of it, but it's cheating a little bit, is just to set the region of interest to only this bit. So usually when I process, say, 100 tomograms, I just import them all at once into the software, just by selecting all of them in a folder and dragging them onto the viewer, and then one by one I go to the first data set and I set a region of interest. This does two things. It makes processing a lot faster, because there is really no need to image these bits. They're only there because essentially the chip on the camera was this size, so you get some extra bits. And secondly, you get rid of predictions like these. So there's an issue here with the low overlap and with the competition with the carbon model not working too well. But by just moving the region of interest over here, fine, right? Sorted. So let's use that. And then what's more? We still get some bits here and there. So there's a pink artifact over here, which again is due to the overlap and can usually be ignored. But there's also a prediction over there. Maybe gone if we increase the region of interest, and a prediction over here, right? So that's not what we want. So what helps there is to use model interactions, and we'll need one that says that if you're close to carbon, you're not allowed to be an antibody platform, because you wouldn't be a great particle for subtomogram averaging anyway. So we can go into the antibody platforms model, interactions tab, and let's open the interactions tab for all of them, and give it an interaction. So you press the plus button. Interaction number 1, we've only got one right now, but they are computed in a specified order. We'll get to that later. And now we wanted to avoid carbon with a radius of, let's say, 30 nanometers. So you get rid of most of that pink stuff over here. Again, we can look at the adjacent slices and see if there's also pink predictions over here. And as you can see, there's some pink stuff here right now, but in the next slice, this one is gone, so that won't be much of a problem. And this one, though, is still there. And one way to fix this is to go back into that interactions tab and say that the threshold for the carbon model in this carbon avoidance interaction must be lower. So you can play around with the threshold for the carbon model. And I'm not too happy with the carbon model, so we should have probably just trained it for longer, or maybe included some more negative examples for the membranes, or annotate this more thoroughly. But it is what it is right now. So with a threshold of, let's see, 0.35, this is alright. Well, this is not great, but it's reasonably useful for a model interaction. And there's no carbon being predicted over here, so we don't need to worry about losing these two for correct predictions. So a threshold of 0.35 is fine. You can control click this slider over here and enter 0.35. The predictions are being updated on the fly, so it can get a little bit slow if you have many interactions and many models. And make the radius maybe 50. Again, a larger radius also makes it a little bit slower. But now we've gotten rid of those false predictions, and we've still got the ones over here as well. Let's add another interaction to fix a problem that we actually don't have right now. But let's say there would be an antibody prediction over here in the bottom somewhere where there really shouldn't be one. We can get rid of it by saying antibodies need to co-localize with the membrane, which they should, right? So again, let's set a fairly big radius to not be too strict, and then set the threshold to, radius of 30. Right, this one is back again, but let's ignore it for now. And then the membrane threshold, set it a little bit lower. There we go. See if we can get rid of this, maybe by lowering the carbon threshold a bit further. Fine. Yeah, that seems reasonable. Okay, now let's see if it actually worked well. So go back into the segmentation tab and find that antibody platforms feature. And let's find the slice where we've annotated a number of antibody platforms. So these things should all be picked up by the models. And before I go there, to sort of preempt the disappointment, they may not be, again, because we've only trained each of these models for about a minute. In the paper we used 50 epochs. I forgot all the timings, but it was usually a bit longer than a minute. But let's see how well it does. Well, there you go. We could play around with the interaction thresholds and all of that a little bit extra. But you can see that these are being picked up quite nicely. So now what we can do is import another data set. I'll just have to quickly find one. Let's see. So importing another one. And it's a bit slow because the first thing that happens is all these models are now applied to the new data set. So let's see. We'll crop it a bit. Let's find the slice we want to actually use. Over here, again, lots of antibody platforms. We've not cropped it yet, but that's fine. And see how well it performs. So these are picked up nicely, as you can see. So there are 1, 2, 3, 4, 5 antibody platforms that are being found. And then there's a clear one here, which we're not finding because it's avoiding the carbon, and the carbon model isn't great. Let's see if we can improve it by just getting rid of the carbon model. But before I do that, and usually that actually shouldn't help getting rid of it, but it's just to give you the example. Before I get rid of it, I'll actually save it somewhere, call it carbon, and then if you get rid of it, nah, not too great, get rid of it, and if you regret it, add a model, click load, open that carbon one, and there you have it again. So you really only need to make a model once, and then you can apply it to any tomogram. Of course, the box size is fixed, and the pixel size is also fixed, because you've trained it on a dataset with a particular pixel size. So now if you want to apply a carbon model to a dataset with let's say 5 angstroms per pixel, which is less than half, then probably this one is not going to work too well. But the software does automatically rescale the input images such that the rescaled pixel size is that which the model expects. Now, of course, if you rescale a 5 apex image to a 13.91, you're going to see lots of interpolation artifacts which mess with the output of the neural network. But it tends to work for the smaller differences between pixel sizes. So anyway, then finally, we'll set a proper crop for this one to ignore all the other junk. Looking fine. And then we go to export. I forgot what name this one had. 58. We'll export 58 using all 3 models. Those settings all look fine. And then one final thing I'll do is go to File and Save Model Group, and I'll call it Antibody Detector. And by doing that, we've saved these 3 models into one group, including their interactions. So if we get rid of all of them by accident, you can just go to Import Model Group, get the antibody detector one, and then all is not lost, because it takes a couple seconds to boot them back up again. But there we go. Platforms are being predicted nicely-ish. See if we can make it a bit clearer to the eye by blurring the data set a little bit, changing the contrast. And then blending in the pink stuff. See? There you go. Decent. So we'll go to export, set some export limits, because again we don't want to process all 350 slices. These datasets are 350 slices just because we've automatically done the tomogram reconstruction, and we didn't want to do the positioning, so just making them a bit deeper ensures that all of the sample is within the tomogram, even if you process 100 different ones with different offsets and messed up eccentric heights and all of that. So fine, this seems fine. Start export. And now it takes a bit longer than before. I can actually check that. The image processing by each of the neural networks for the VGGNet is about 150 milliseconds or 200 milliseconds, and for the UNet it is 180 milliseconds. So it's about half a second per cropped image per slice. But then on top of that we get the model interactions, which can be a bit slow when the radius of the interaction is set to a very high value, like 30 nanometers in this case. But we're getting there, and I'll append a 3D model of the results to the end of this video.